Modern aircraft are, without a doubt, some of the most unbelievably complex machines humanity has ever built. And every single day, engineers are on a quest to make them even safer. So today, we're going to dive into a breakthrough that could totally revolutionize how we keep an eye on a plane's health. We're talking about moving from those old-school periodic checkups to a constant, real-time conversation with the aircraft itself. Let's see how they're pulling it off.
Okay, so before we can even get to the cool solution, we've got to understand the problem they're trying to solve. And that problem is all about the invisible threats that every aircraft faces on every single flight.
Just imagine for a second the incredible forces a plane has to deal with. You've got the stress of takeoff and landing, you've got turbulence shaking it around at 30,000 feet, not to mention things like tiny impacts or just the general wear and tear from getting older. And all that stress, it can create these tiny, microscopic flaws, little cracks or deformations that are completely invisible to the naked eye. But they have the potential to grow into really serious problems. So the big challenge is, how on earth do you find a problem that you literally can't see?
Well, the answer comes from a concept called structural health monitoring, or SHM for short. And the key word, the absolute game changer here, is continuously. Instead of just looking at the plane when it's on the ground every few months, SHM is all about giving the structure itself a voice, a way to report on its own health in real time while it's actually flying.
You know, the easiest way to wrap your head around this whole thing is with a really powerful analogy. What these researchers are building is, for all intents and purposes, a nervous system for the aircraft.
What if a plane could do more than just fly? What if it could feel? Just think about it. What if it could actually tell engineers, hey, I felt a little too much strain on my left wing during that last patch of turbulence. Or maybe there's a weird vibration coming from near the engine mount. That's the dream. That's the goal.
And to make that happen, you've got to give the plane senses. In this system, it gets 4 different kinds. You've got strain gauges, which act like nerve endings in our skin, feeling any stretching or compressing of the plane's structure. Then there are accelerometers, which are kind of like our inner ear, sensing all the vibrations and motion. Thermistors are there to detect temperature, which can really affect the materials. And finally, you have these super-sensitive PZT sensors that can pick up the high-frequency ping of a tiny impact or a crack just starting to form.
So you've got all this data pouring in from the plane's brand new nervous system. But where does it all go? I mean, what do you do with it? Well, this is where things get really, really cool. All that information is funneled into building the aircraft's digital twin. Now, don't just picture some fancy 3D model. A digital twin is so much more than that. It's a living, breathing virtual copy that is updated in real time with data straight from the physical plane. Every bit of strain, every little vibration, every temperature shift on the real aircraft is mirrored instantly in its digital counterpart. It's basically the ultimate high-fidelity avatar for the airplane. And look, this slide right here proves this isn't just some sci-fi dream. It shows you the actual progression of the technology through what are called technology readiness levels, or TRLs. You can see it starts way over on the left as just an idea, a concept. Then it moves through lab tests and simulations and goes all the way up to TRL 5. That's where it's being tested and validated in actual flight tests. This is real, and it's happening right now.
So the concept is awesome, right? But how does it actually work? Like, how do you get the data from a tiny sensor on a wing all the way to this digital twin that lives in the cloud? Let's trace the path. Okay, from a bird's eye view, it's kind of like a 3-step dance. First, you have dozens of these small sensor nodes scattered across the aircraft in all the important spots. They're the ones collecting the data. Second, they wirelessly send all that information to a central onboard gateway. And third, that gateway beams everything up to the cloud. Simple as that. All right, now let's zoom in a bit. This diagram lays out the entire journey for us. It all kicks off on the left with the sensing skin, which is just the network of sensors generating the raw signals. From there, a tiny computer chip, a microcontroller, chews on that data right at the source. Then it gets passed to the onboard gateway you see there in the middle. And finally, whoosh, it's transmitted to the cloud, where the digital twin is living and constantly updating itself. And what's so cool is that each one of these little sensor nodes, it's basically its own miniature computer. It's got a CPU for a brain, the sensors for its eyes and ears, a little module to communicate, and its own power. This modular design is just brilliant because it means the whole system is super scalable. You want to monitor a new part of the plane? No problem, just add another node.
And here it is. This is the actual hardware. This isn't just a diagram anymore. This little discovery board is the heart of the sensor node. It's not some giant, heavy box. It's compact. You can see the main chip right there, the brain.
And all the spots where the different sensors plug in, plus the wireless module. This is tangible, real-world tech.
So let's talk about what happens inside that tiny board. It's like a little assembly line for data. First, the raw physical signal comes in from the sensor. The board's first job is to clean that up and convert it into a digital signal that a computer can actually read. Then it's quickly shuttled into memory so that not a single piece of data gets lost. And finally, it's sent out wirelessly. It's a perfectly smooth journey from the physical world to the digital one.
Okay, so the theory is solid, the design is brilliant, but, the million-dollar question is always, does it actually work in the real world? To find out, the researchers put the system on real planes and took to the skies. So to find out, they took the system and put it on these real F-door aircraft, a Cobra and a Sports Star. And as you can see in the diagram, they didn't just stick these sensors on randomly. Oh no, they were strategically placed at known critical locations. We're talking wing spars, engine mounts, tail stabilizers, all the places where stress is most likely to build up.
Now, while they were up there flying, they had to solve a really crucial puzzle. It's kind of like recording music. If you record at too low a quality, you miss all the high notes and everything sounds muddy. But if you record at super high quality, you end up with a file that's just enormous and impossible to manage. So for an aircraft, what's the perfect recording speed?
Well, the magic number they landed on was 1,000 hertz. That means the system needs to take a measurement from the sensors 1,000 times every single second. That gives it a crystal clear picture of what's happening without creating a tidal wave of data.
In this chart right here, it shows you exactly why that number is so critical. It's showing the error rate when they try to calculate the plane's remaining lifespan based on different speeds. Look at the bar on the left. If you sample too slowly at 500 hertz, you get a huge error in your safety calculation. That's bad. But look what happens when you hit 1,000 hertz. That error drops like a rock. It's the perfect sweet spot between getting great data and not having too much of it.
So, let's zoom out. What does all of this really mean for the future of flying? Well, it's a huge deal. It represents a fundamental shift in how we even think about aircraft safety.
What we're seeing is a massive shift, a move away from scheduled maintenance and into predictive maintenance. The old way is like changing your car's oil every 5,000 miles, right? You do it whether it needs it or not because that's what the schedule says. The new way, the one powered by digital twins, is like having a smart sensor in your oil that tells you exactly when it needs to be changed based on how you've actually been driving. It's just smarter, it's more efficient, and at the end of the day, it's a whole lot safer.
And hey, don't just take my word for it. The researchers who developed this said it best. They state that this whole approach has the potential to cut down the cost and time of manual inspections, and by doing that, it reduces the risk of failure. And that, right there, is the holy grail of aerospace engineering.
And that really leaves us with this incredible, mind-blowing question at the end of it all. This technology, this idea of creating a real-time, sensing digital replica of a complex system, it's not just for airplanes. So what's next? Could we give a nervous system to our bridges so they can tell us when they're under too much strain? Or to our power grids to predict a failure before a city goes dark? Maybe even, one day, we could build a digital twin of a human heart, one that could warn a doctor of a heart attack before it ever happens. The possibilities are absolutely staggering.